The industrial production of sulfuric acid involves several steps. One of these steps is the reaction of sulfur dioxide, SO2, with oxygen to form sulfur trioxide, SO3. This means it's a reversible reaction. What volume of sulfur trioxide in decimeter cubed is produced by the complete reaction of 750 decimeter cubed of sulfur dioxide? All volumes of gases are measured under the same conditions of temperature and pressure. Right, what may seem like a difficult question is actually very, very easy. All you have to do is pay attention to these numbers here, or the absence of these numbers. So 2, 1, 2. So that's the ratio. So if you have 2 parts of sulfur dioxide reacting with 1 part oxygen in this equation, not if, but you will get every 2 parts sulfur dioxide are reacting with 1 part oxygen, you get 2 parts sulfur trioxide. So in other words, what volume of sulfur trioxide in decimeter cubed is produced and using 750 decimeter cubed of sulfur dioxide? So 750, you'll also get 750 because the ratio is 2 to 2, simplified 1 to 1, so you get the same amount. The answer is 750. Next, calculate the volume of oxygen needed to react completely with 750 decimeter cubed of sulfur dioxide. Okay, so again, same temperature and pressure. It'll always say that, so you don't have to worry about it. There's no strange conditions that affect your answer. So, if this said 2 here as well, then it'd have to also be 750. But what we're saying is you need half as much oxygen to react with this successfully to produce that much. So you just halve 750, which will be 375. Because the ratio of in the balanced symbol equation, the ratio is 2 moles to a ratio of 1 mole. So you have half as much. So it's half of 750, which is 375. Calculate the mass in kilograms of 750 decimeter cubed of sulfur dioxide measured at room temperature and pressure. Relative formula mass is given to you. 1 mole of any gas at room temperature and pressure occupies 24 decimeter cubed. So this question requires a number of steps. You're going to need this equation, mass divided by formula mass equals number of moles, and it will need to be rearranged to mass, because remember we're trying to work out, calculate the mass in kilograms of 750 decimeter cubed of sulfur dioxide. So it's a gas, but what mass is it? Mass equals formula mass multiplied by number of moles. I think it's probably a good point to just refresh your memory that moles is just a number of atoms, and if you have 1 mole of any substance, it equals the relative atomic mass of that substance, or the formula mass, in grams. So for example, the relative atomic mass of magnesium is 24 if you look on the periodic table. If you have 1 mole of magnesium, then you have 24 grams of magnesium. So, for example, if you had 24 grams of magnesium, right, you would have 1 mole, because 24 divided by the atomic mass 24 is 1. If you had 48 grams of magnesium, then you'd have, divided by 24, 2 moles. Okay, so that's what this equation means. By dividing the mass, the real mass of how much you have of an element, by its formula mass or its relative atomic mass, you basically know how many moles. To give you one more example, carbon dioxide has a formula mass of 44. If you add up carbon 12 and then you add up 2 oxygen, 16 plus 16, you get 44. So if you had 44 grams of carbon dioxide, because the formula mass is 44, you have 1 mole of carbon dioxide. That's how many atoms you have. If you had 88, then you'd have 88 grams of carbon dioxide, and you'd have 2 moles. Just a quick lesson on moles. But here's a different sort of problem. How many moles do you have in 750 decimeter cubed? That's a volume, that's not a mass. Well, the sort of way to work it out is what it tells you here. 1 mole of any gas at room temperature and pressure occupies 24 decimeter cubed. So how many 24 decimeter cubes go into 750? That'd be how many moles, because this is 1 mole. So you simply divide 750 by 24, and that gives you 31.25 moles. So now we have the number of moles. We also have the MR, which is given here. So we've got number of moles and MR, so we just need to multiply the two together to work out the mass. And if we do that, we get 64 times 64 from here times number of moles from here, which will give you 2,000 grams, but the answer has to be in kilograms because it says here, so 2 kilograms. Yeah, it's important to note actually this equation here gives you the answer in grams, so if it's asking for kilograms you must convert it. That's really important to remember. Okay, for my money, I think this is the toughest 6-mark question I've seen in an exam, mainly because it is hard to access. It requires a lot or high level of scientific literacy, and if you don't understand the question, it's really difficult answering it. So let's have a look. The reaction to produce sulfur trioxide reaches an equilibrium. So here's the reversible reaction. Whenever you're looking at equilibrium, you're looking at reversible reactions, and there's the two-way arrow to tell you it's a reversible reaction. So just as sulfur dioxide and oxygen combine to make sulfur trioxide, this can also dissociate and form the reactants again. So the forward reaction this way is exothermic. It releases heat. The rate of attainment of equilibrium and the equilibrium yield of sulfur trioxide are affected by pressure and temperature. Now, instantly you're hit with two very loaded sentences. You need to understand what this means. So the rate of attainment of equilibrium is basically saying how quickly the state where the rate of the forward reaction equals the rate of the reverse reaction is achieved. So how quickly until both these reactions, the forward one and the backward one, are occurring at the same rate. To make this easier for your brain to sort of compute, in other words, anything that increases the rate of reaction will increase the rate of achieving this state. So any factor which will increase collisions between particles will increase the rate of attainment of equilibrium. And the equilibrium yield of sulfur trioxide is just basically how much desired product is produced. So yield is how much you get, and that's just another way of saying how much desired product is produced. So these graphs summarize both these ideas. So firstly, you can see that as a chemical reaction starts, you have your reactants and you have no products. So they start to react and react and react and react, and you're getting more and more product produced. But now, because there is product and more product is building up, you're going to start to get the reverse reaction. So the products are now basically reversing to form the reactants. After a while, you get a certain amount of reactant being used up to make the product, and then the product forming the reactant again. And there'll come a point where this starts happening at the same rate. So when that happens, we've attained equilibrium. That's equilibrium rate. So how quickly this happens, this process here, like whether it's like this or like this, that is the rate of attainment of equilibrium. Whereas how much does the equilibrium yield is basically how much of the desired product we are making. So you can see as reactants are used up, we're making products, but because products will eventually undo themselves and become reactants again, only so much product will be made. So this is how much is being made of the desired product. It won't change because it keeps on undoing to become reactants. So this is the equilibrium state. Notice how the rate is the same, so they'll both achieve the same rate, but you can have more product being produced than reactant, and ultimately we want more product than reactant. That's favourable. That will help you make money from your reaction. A manufacturer considers two sets of conditions, A and B, for this reaction. In each case, sulfur dioxide is mixed with excess oxygen, so you've got plenty of this, you don't need to worry about that. The manufacturer changed the temperature, the pressure, and only used a catalyst in B. The set of conditions in A and B are shown in figure 7. So you can see this one's got higher pressure, but lower temperature, and this one is using a catalyst, whereas this one has lower pressure, higher temperature, and no catalyst used. So the manufacturer chooses set of conditions in B rather than the set of conditions in A. So they are favouring this set of conditions. Explain by considering the effect of changing the conditions on the rate of attainment of equilibrium and on the equilibrium yield of sulfur trioxide, why the manufacturer chooses the set of conditions B rather than the set of conditions A. We'll just go through this one at a time. So firstly, let's deal with temperature. Remember what I said, that anything that increases the rate of reaction increases the rate of attainment. So temperature here A, equilibrium is reached much faster, or the rate of equilibrium is reached much faster under condition A, where the temperature is higher. But we need to explain why. Because the molecules have more energy in their kinetic store, increasing the frequency of successful collisions. In other words, they're moving faster, they're going to collide with oxygen and produce sulfur trioxide. However, equilibrium yield of sulfur trioxide is greater under condition B, where temperature is lower. And this is because in a reversible reaction, any change imposed on the reaction will try to be reversed, there'll be a pressure on the reaction to reverse that change. So this is an exothermic reaction. The forward reaction is exothermic, so this produces heat. Now, if you, for example, increase the heat, that would slow the rate down of the forward reaction. It would favour the reverse reaction because you're trying to get that balance of heat, because you're upping what's already there, so this will try and undo that change. But by choosing a lower temperature, by lowering the temperature, you're favouring the forward reaction. So, as lowering temperature favours the forward exothermic reaction, but under these conditions, obviously, it will take longer to reach this equilibrium because things are moving slightly slower, but you will get more product. So you'll get more equilibrium yield, but it will take longer to reach equilibrium. In other words, more this, but this will be slower. Next, pressure. Higher pressure in set B causes equilibrium to be reached faster as molecules are brought closer together, increasing the frequency of successful collisions. Yield is higher under set B as reactants occupy greater volume than products. 3 moles versus 2 moles, so increasing pressure favours the forward reaction. So what I mean by that, on this side, you have 3 moles of particles, 1, 2, and 3 for the oxygen. On this side, you only have 2. In other words, you have way more particles on this side than this side. So if you increase pressure, the same pressure on both sides, it's going to favour the side which has more particles because it'll be crammed together and it will encourage reacting. So higher pressure in this case will actually cause equilibrium to be reached faster and will also increase equilibrium yield. Finally, the catalyst, less energy is needed for reactions to occur. So that's what a catalyst does. So it increases the rate of the forward and reverse reaction. So catalysts will not favour forward or reverse because they increase the less energy is needed on both sides. Equilibrium is reached faster, but there's no change in yield because the forward reaction and the reverse reaction now happening just faster. But you can say lower temperature will be needed, so you can actually make this reaction operate at a lower temperature because of the use of a catalyst. Take your time to examine and analyse this question because it does require a lot of thought and thinking. It's a tough question.